it's me, Tim Dodd, the everyday astronaut. Liquid-fueled rocket engines operate by flowing fuel and oxidizer into a combustion chamber at ridiculously high pressures in order to throw as much mass out the flamey end of the rocket as quickly and thereby as efficiently as possible. But how does it get that way? How on Earth, and even more difficultly, how off Earth, do you get an engine up to operating pressures and temperatures? Engines often utilize pumps which themselves rely on the engine to be running in order to get power. And having a rocket engine run and getting a rocket engine running are two wildly different things. There's often an extremely delicate dance to get the pumps, valves, temperatures, and pressures all up to operating conditions perfectly. Get it wrong by just a few milliseconds even, and you can cause a detonation that can completely destroy the engine. So today we're going to do a deep dive on how exactly you start a rocket engine. We'll cover pretty much everything from a simple solid rocket motor to all of the intricacies of liquid-fueled rocket engines, including thermally conditioning the engine, the spin-up process, the scary transient regions, and the actual ignition of the propellants. Then we'll talk about some of the extra challenges like starting a rocket engine in space, and then we're going to actually go step by step inside a rocket engine during its startup. Now this is a very long video, so here's the timestamps for each section, and we've got the YouTube timeline broken up into those sections too. By far the easiest rocket to start has to be a solid rocket motor. In fact, there's actually a good chance that you've done this yourself. If you've ever launched a model rocket or even fireworks, you've already pretty much experienced the ignition sequence of a solid rocket motor. Solid rocket propellant is exactly what it sounds like. It's a solid that is rocket propellant. It's usually like a sludge of premixed fuel and oxidizer, and all it takes is energy to get the combustion process started. In the case of a small model rocket motor, that energy usually comes from the heat from a set of small wires. Bigger solid rocket motors will usually require more energy to get started, so sometimes they'll have some black powder, which is basically gunpowder, that will initially ignite from the wires, and then a chain reaction will occur that will then light the solid propellant, where it will continue to self-sustain. But once you start talking about large orbital class solid rocket boosters like those on the space shuttle, or maybe those on the Space Launch System, otherwise known as the SLS rocket, which is at the heart of the Artemis program, there's basically a bomb sitting on top of the booster that starts the ignition process. There's a device called a NASA Standard Detonator, or an NSD. And this is a little device used since the Gemini program for things like separation events on booster separation and fairings and frangible bolts, or in this case, they're the device that they actually use to start the chain of reactions that'll get these massive solid rocket boosters going. When it's go time, a signal is sent to not just one NSD, but a completely redundant NSD to ensure the boosters light. After all, if one doesn't light, it would be very, very bad. And don't forget, once you light a solid rocket booster, there is no shutting it down. The NSDs burst through a thin barrier seal, which then lights a pyrotechnic booster charge. Then that booster charge is what ignites propellant inside an igniter initiator, which then lights the main booster igniter, and that lights the entire surface of the core of the booster virtually simultaneously. So for a little overview here, it's basically a waterfall of explosives that cascade down from the top of the booster until eventually the entire booster is lit, pretty much all at once. Basically stepping up from a small charge to a medium charge to a large charge to booster ignition. Like I said, it's basically more or less a bomb that's lit at the top of the booster, or otherwise known as the forward segment, that starts the ignition process. It's really just about that easy. Just because you combine your fuel and your oxidizer doesn't mean you're going to get combustion. In fact, most propellants, due to the dismay of rocket engineers, will kind of happily coexist in the same space and may even exit the system without unleashing their fiery goodness at all. Or even worse, they may accidentally ignite at the wrong time or place, which is often catastrophic. Perhaps you've heard the term hard start. This is basically when the propellants combust at the wrong ratios or perhaps at the wrong time or place. The worst hard starts can severely overpressure the engine, or maybe overspin the turbines, or cause an energetic detonation that can completely destroy the engine and sometimes even the test stand and or the rocket that they're actually attached to. So the timing and precision of ignition is vital. Like most engines, rocket engines typically require an external source of ignition to begin the combustion process. So what if you actually could just use a chemical reaction to start the ignition process? This is actually pretty common and extremely effective. In fact, if you've ever seen a Falcon 9 or Heavy launch, you may have noticed a green flash right at the beginning of ignition. That, my friends, is the injection of a pyrophoric ignition fluid coming in contact with oxygen to begin stable combustion. Pyrophorics are a type of hypergolic. It's a fluid that will spontaneously and virtually instantaneously react with oxygen. So just inject some pyrophoric fluids into the combustion chamber along with oxygen, and ta-da, you've got yourself a flame. SpaceX uses an ignition fluid called TTEB, or triethyl aluminum triethylborane. It's stored in their own canisters on board the rocket and allows for multiple restarts of their Merlin engines. Now, not every engine is connected to a TTEB canister, only the engines that would do a relight. So 3 of the 9 Merlin engines on the booster and the vacuum Merlin engine on the upper stage. But on the ground, the Falcon 9 and Falcon Heavy are lit using ground-supplied TTEB, because why not keep those systems and their weight on the ground if you don't need to carry that mass off the launch pad? Before you get a liquid-fueled rocket engine running, it has to be prepared for the ludicrous temperatures it's about to face. And believe it or not, I'm not talking about the extreme heat. I'm actually talking about the extreme cold. Not only do most orbital liquid-fueled rocket engines run propellant through the walls of the engine to keep the combustion chamber and nozzle from melting, but the pumps themselves will flow upwards of thousands of liters per second of cryogenic propellants, which can make the metals, valves, and bearings brittle and failure-prone. This, of course, is specifically true of any engine that uses cryogenic propellants. So any liquid oxygen, also known as LOX-powered rocket engine, and especially those that run on hydrogen or hydrolux and methane or methalox for their fuels, which are also cryogenic propellants. These propellants all make up the majority of rocket engines that we see on orbital rockets. But before you even begin to chill down the engine with the propellants, you need to purge the engine from moisture and air pockets, and this is usually done with nitrogen. If there's any water vapor in the lines before cryogens are introduced, it'll freeze and cause damage to the engine, with the potential for clogged orifices, damaged seals, clogged injectors, etc., etc. But if it's a hydrolox engine, liquid hydrogen is so cold, it can even turn any residual nitrogen into a solid block of ice and do all of the bad things we just mentioned. And an ice blockage can be really hard to investigate because the evidence of the root cause of the failure melts away by the time a human can even get close enough to investigate. Because of this, hydrogen-powered rocket engines are usually purged with another inert fluid, helium. Purging and chill down of the engines can be anywhere from a few hours before launch to a few minutes, but this varies very much from engine to engine. So listen for something like engine cool down or engine chill down called out on comms.
One engine chill has started.
All right, there's that call that stage 1 engine chill has started.
Okay, so once the engine has been purged of moisture, we can start to actually thermally condition the engine with the cryogenic propellants. This process involves opening what's known as a pre-valve, which is the big valve that connects the engines to the propellant tanks. The propellant will fill the pumps and fill all the way down to the main valves, which is usually one or a number of valves for fuel and oxidizer. Then the pumps will just soak in a bath of cryogenic propellant until the pumps eventually get down to those frigid temperatures. In comparison to cryogenic propellants, the engine is actually scorching hot under normal, everyday, human, comfortable ambient temperatures. Even if an engine was hanging out in Antarctica during a deadly blizzard, it would still pretty much immediately boil off any cryogenic propellant that touches it. So there needs to be a vent line to remove the boiled off propellants. Oxygen can usually just be dumped overboard, which poses little to no risk when being vented into the atmosphere. But in general, a cryogenic fuel that now has boiled off into a gas like methane or hydrogen needs to be recaptured and either rechilled and pumped back into the rocket, or it can be vented away from the rocket in a controlled manner where a flare can prevent a buildup from accidentally detonating. Because if you just vent gaseous methane or hydrogen out into the atmosphere in an uncontrolled manner, don't expect very good things to happen. This is why you see those giant sparklers lit before Space Shuttle, SLS, or Delta IV Heavy launches. It's not to light the actual engines and start combustion. It's to burn off the gaseous hydrogen that will exit the engine during the startup process before main combustion chamber ignition. These are called radial outward firing initiators, or ROFIs. They're just preventing a large cloud of hydrogen from gathering and potentially detonating. Getting an engine down to operating temperatures is absolutely vital, and it's monitored very closely by the engine's computers that run the engine. In fact, it was a fear that one of the RS-25s wasn't cooling down prior to ignition that caused the first scrub of Artemis 1 on its very first launch attempt in August of 2022.
It's a scrub.
It is officially a scrub?
Officially.
All right.
Launch director called it.
Launch director called a scrub.
Engine number 3's temperature sensor wasn't showing the engine had cooled down enough to the required temperatures, so the launch attempt was scrubbed for the day. It turns out the engine was likely indeed at the right temperatures, but the sensor itself was erroneous. But it just goes to show how important engine chill down is. If an engine's not cooling down as expected, no diligent launch conductor would proceed towards liftoff.